Video for Edexcel Corpio 1 Chapter 2. This is Argand diagrams. We touched on this briefly in the last video revolving around complex numbers. So we're going to start with this part of the spec. Again, we started this before. Argand diagrams, just a graph to show complex numbers. So you've got the real axis here, imaginary, and you plot the complex numbers as so. So if you had 3 plus 4i, 3 on the real axis, 4 on the imaginary axis, just this. It's not too complicated. Okay, so the complexities actually increase because now we're going to be talking about loci. Okay, so 3 main types of loci that we need to worry about. So this is going to be your circle. This is your perpendicular bisector. And this is your angle. It just makes a line. We'll go more in depth later on. We'll start with circle for now. Just as an example, we'll say z minus 3 minus 4i, just like we had before, is 3. We'll call it. So we can actually rewrite this as z minus 3 plus 4i. See, we can expand this out. You'd get the minus 3 and minus 4i equals 3. So what this gives us a circle where this complex number here, this is our center, and 3 is our radius. So our diagram will look something like this. We have 3, 4i. This is our center. 6, 0. 4 will be 1 and 7. And that is our locus. Actually, that's not our locus. Our locus would just be this. If we had this, there is less than 3, then we would shade it in to give us the range of values where our complex number would lie. Another thing to look out for, if I gave this example on purpose, because a lot of people sometimes, they might think that the center would be minus 3, minus 4i. But what we're actually doing is we find the distance from any complex number z from our center to get the locus. So we're going to have to do z minus whatever we have here. So that will give us 3 plus 4i, which would then give what we have here. The next loci that we need to worry about, the next sort of genre of loci, is this. This is our perpendicular bisector. So we'll just do what we had before, z minus 3 plus 4i, and so equal to z minus 2 plus 5i. Fine, we can do that. So our diagram will look like this. Actually, no, let me do 5 and 2i. 5, 2. Okay, so these are 2 points. Our actual locus is going to look like this. So this is our perpendicular bisector, and that works because this bit, it tells us that the modulus is going to be equal. So that's the distance between each of these points from our complex number, which is going to lie on this line. And because of that, that's why it's going to be a perpendicular bisector, because by definition, these distances have to be equidistant. Likewise, if we said z minus this would change our position of our complex number, because it would then be closer to this side. There would be this bit that's shaded. This seems a bit counterintuitive because it says that z minus 3 plus 4i is greater than this. But actually, if we have a complex number here in this range, the modulus, the distance from 3 plus 4i is going to be greater than it is from 5 plus 2i, which is why this works. So, okay, so we've got argument, we'll use our same value as before. Z minus 3 plus 4i is, let's call it pi over 4. You might be familiar that this is equal to 45 degrees. So I'll start like so. Then 3 and 4. So you can start like this. And our angle is actually we're going to have a horizontal here because we want to measure our angle from the horizontal. So don't care about anything here. So our line is just going to be this. It's going to be our pi over 4 angle. The reason that we have this half line here, that's why it's called, because if we worried about having angles here, then it wouldn't be from this positive axis. The angle would actually become negative. That's our reason here. Okay, the last thing I think I should cover is converting from all of these from complex to Cartesian, because that helps a lot in finding solutions where we want a complex number that meets both conditions. Two or more conditions where we have maybe a circle or a perpendicular bisector, anything like that. So if you've got a circle here, this is fairly obvious. We're going to have x minus 3, our real component, squared plus y minus 4 squared equals radius squared, which is 9. Okay, for this perpendicular bisector, this is just your simple GCSE stuff, finding the equation of perpendicular bisector. So we've got our midpoint being 4, 3. Gradient is 3, 4, 2, so that's minus 2, 2. Gradient of this is minus 1. So our perpendicular bisector have gradient of 1, it's negative reciprocal. Y equals x plus c. 4, 3. Okay, so y equals x minus 1. It's our perpendicular bisector, meaning my diagram here is actually a little bit inaccurate. Minus 1 look a bit like this. Okay, last one. For the angle one, this is the only one that might be a bit difficult. So the way I like to get my gradient, so we've got this value here, right? So this is, we'll call the 1 pi over 4. And what I want now is this, the opposite side. So the reason I put it over 1, because then I can get x over 1 to get my gradient, which is what I want. So we can use tan pi over 4 is equal to opposite over adjacent equals x. So tan pi over 4, which is just 1. So our gradient is just going to be 1. X plus c. Then we've got 3 plus 4i. Again, y equals 3 plus 1 plus c. c is equal to 1. That means this line right here will be y equals x plus 1. Then I'll write both these values in Cartesian form. So the circle will be x minus 3 squared plus y minus 5 squared equals 2r whole squared, which is 4r squared. The line, actually, I'll do what I did before. We've got this triangle here, pi over 4. We'll call this 1. So this also has to be 1. Tan pi over 4 to 1. Fine, that's all good. So our gradient actually is going to be minus 1. Because remember, this line's going down. It's going to be like this. So our line will be y equals minus x plus c. And we can say y equals minus x plus 2 will be our line. Is this going to be 2, as our x-intercept is 2 as well. Next, I'll find a solution to this equation. So we have x minus 3 all squared plus minus x. Then 2 minus 5 is minus 3. So minus x minus 3 all squared equals 4r squared. Squared minus 6x plus 9 squared 6x plus 9 equals 4r squared. This will be 2x squared plus 18 minus 4r squared equals 0. Because I brought this to the other side. Now, the question says, two distinct complex numbers. So there are two real roots. So our discriminant must be greater than 0. I'm going to work with that. So our quadratic was 2x squared plus 18 minus 4r squared equals 0. So b squared minus 4ac is greater than 0. So 0 minus 4, 2, 18 minus 4r squared is greater than 0. We have 32 r squared minus 144 is greater than 0. So our solutions would look something like this. So it's minus 3 root 2 over 2, 3 root 2 over 2, and it would be these sides. So obviously we can't have a negative radius, so I have to get rid of this. So our range for now is 3 root 2, 2, then r, okay. That's fine. However, this isn't actually our final answer. Something I've noticed right now is that this Argand diagram right here is incorrect. The question asks for two distinct complex numbers that satisfy these values. Here I've only got one solution. So my diagram would have to look something like this. So here now we've got two solutions. And this works because the circle starts before the start point of our line here. Remember, our actual locus is this. It won't go down like this. This is our actual angle. This will give us our 3 pi over 4. So the absolute maximum radius that we can have is when the circle meets this point, 2, 0. Because that's only case that we can start to have two solutions. So our maximum radius is going to be 2, 0, and our center is 3, 5. If this is going to be 2r, 4r squared equals 5 squared, 5 and 1, 5 squared, 1 squared. So 4r squared equals 26. R squared equals 26 over 4. R equals root 26 over 2. That means our maximum value can only be root 26 over 2. This is our final inequality. So our next question, I'll put this in modulus argument form. So on modulus first, so that's 4 root 3 squared plus 4 squared. So that would give us 8. That's our modulus, our argument diagram here. 4 root 3 minus 4. So this is going to be our angle. So we can just do tan plus minus 4 over 4 root 3. And that is minus 1 over 6 pi. So our final form is 8 cos minus 1 over 6 pi plus I sine minus 1 over 6 pi. Perfect. I'll be asked to sketch this on the Argand diagram. We've done the first bit, so that's 4 root 3 minus 4i. So that's our w. Point defined by arg z plus 10i. Which is, so that's basically just z minus 10i, obviously. So we've got minus 10i down here. Let's extend that, minus 10i. Let's look something like this. Our half line here. And you might recognize that pi over 3 is just 60 degrees. So this is pi over 3. Last bit, the minimum distance from the locus. So that is just a perpendicular distance, this to this. I think it's easier just to put all of this in Cartesian form. So this line, the one we have arg z plus 10i, this is, so we've said before, this is pi over 3, 1, so tan pi over 3 is root 3. So this line is y equals x root 3. So our gradient minus 10, as the y-intercept is 10i. It's 10. Yep. For our perpendicular lines from W to wherever, the gradient is going to be negative reciprocal. Y equals minus 1 over root 3 x plus c. So our point is 4 root 3 minus 4i. So minus 4 equals root 3 or root 3 plus c. You'll notice that this is equal, so c is actually 0. So the second equation is just simple. Y equals minus 1 over root 3 x. Perfect. So we'll set that equal to each other. So minus 1 over root 3x equals x root 3 minus 10. 10 equals root 3 plus 1 over root 3, which is just 4 for root 3. 4 root 3 over 3, sorry. That's 4 root 3 over 3. X equals 2. 5 root 3 over 2. Perfect. This means y is equal to minus 5 over 2. Yes, root 3's cancel out. So our point is 5 root 3 2 minus 5 over 2. And we want the distance from that to w, which is 4 root 3 minus 4i. So this is just Pythagoras. 5 root 3 minus 2 minus 4 root 3. It's all squared. Plus minus 5, 2 minus 4. This all squared. Square root all that. That gives us, so this would be 9. Square root of 9 is 3. So distance, quite simple, is just 3. Okay, for this last question, we've got points we need to find the values of A, B, C, and D. Okay, so A is first radius. We can see that would be 1. A equals 1. We can find D as well. D is this large radius, which is 2. So D is equal to 2. For B and C, radius is minus 2, 1. So Z minus 2 plus I. Z plus 2 minus I is what we want. So B equals 2, C equals minus 1. Perfect. Okay. Part B says we've got this and this perpendicular bisector locus. So Z minus I, Z minus 3I. So it's these lines that we need to worry about. Perpendicular bisector is this. And it says it's greater, Z minus 3I is greater than this. So we want this area, the one further from 3i, because that means the modulus would be greater. With this range that we want, first I think we can find this bit of the circles, so that would be, so we've got semicircles, right? So pi r squared over 2, so that's pi 2 squared over 2 minus pi 1 squared over 2, which is 2 pi minus pi over 2, gives us 3 pi over 2. That's fine. Next, we want to look at this bit. So we need these parts, but I want to get rid of this bit. So I think we can make this a triangle first. So you can find the area of this segment minus the area of this triangle. So the segment we can do as half r squared theta. This is obviously 1/3 of a circle, so angle is going to be 2 pi over 3. So half 2 squared 2 pi over 3 gives us 4 pi over 3. Then this triangle is half AB sine C, half 2 sine theta, sine 2 pi over 3 is just root 3. So the area of this segment here is going to be 4 pi over 3 minus root 3. Then to get rid of this segment, we can just do our original area, which was for the half, which is 3 pi over 2 minus 4 pi over 3 plus root 3, because we're minusing this. That will give us 1/6 pi plus root 3. If we add the 3 over 2 that we had before, this bit, plus 3 over 2 pi, that gives us 5 over 3 pi plus root 3. So our final answer. Perfect. Hope that made sense. Thanks for joining.